I've sketched the cylindrical capacitor in this problem. The two cylinders each have a length L of 2.80 meters, and we're told the inner and outer radius of the two conducting cylinders. We're also given the potential difference, delta V, between them, with the inner cylinder at the higher potential. Part A asks us to find the capacitance per unit length. We can use the definition of capacitance and substitute in Q over delta V, which gives us this expression, and then work out an expression for the potential difference delta V. We know the electric field is directed in the radial direction from the positive plate to the negative plate, so it's everywhere pointed like this, and the potential difference is the line integral of this electric field from the inner plate to the outer plate. Gauss's law tells us that the electric field has a magnitude of lambda, the charge per unit length, divided by 2 pi epsilon naught r. That electric field is parallel to the radial direction from r1 to r2. So when we integrate this and substitute lambda equals q over L, we get this result, which we can substitute into the expression above, canceling the unknown charge and the length of the cylinder. The capacitance per unit length, then, is 2 pi epsilon naught divided by the natural log of the ratio of the two radii. When we substitute all the known values, including this for epsilon naught, we find that the capacitance per unit length is 1.2 times 10 to the minus 10 farads per meter. That's 120 picofarads per meter. Part B asks us for the charge on both conductors. The magnitude of charge is C times delta V, the potential difference, which we can write as capacitance per unit length times the potential difference delta V. We know all those values, so when we substitute them and calculate, we find the magnitude of the charge is 120 picocoulombs. The inner cylinder at the higher potential will have positive charge Q, and the outer cylinder at a negative potential relative to the first will have negative charge of the same magnitude.